I am Kevin Mahaffey. This is my colleague John Herring, and we're here today to talk about mobile applications. It's great to see a whole mobile track here at Blackhat this year. It's certainly a sign that mobile applications are more and more important in everyone's daily lives, and happy to talk about it. So you can find me on Twitter, Drop-All-Tables. Generally our background is we like to talk about mobile security, RFID, privacy, things that matter to people, new technologies. We have a bent for wireless technologies. We've talked at Black Hat, DEF CON, Blue Hat in the past on a variety of topics. And most of all, it's fun, and we hope that some of you guys here today can take what we're talking about and apply it to your personal safety, where you work, if you're a software developer, and building better products to protect people. And ultimately, that's our goal here.
So hopefully a few of you saw our talk last year. We talked about hacking the iPhone and a number of other different mobile platforms. Kevin, myself, and Anthony Lineberry talked a little bit about fuzzing mobile. So instead of looking at the mobile OSs in and of itself, what we're going to be looking at is mobile applications. And really what we've been seeing is an explosion in adoption of mobile applications. In doing so, we asked ourselves, okay, these are actual practical things that people are interacting with every day. Given that, are there actual practical attacks and vulnerabilities that can be discovered, and things that can be learned both for the OS vendor perspective as well as the developer perspective, more importantly. So let's kick things off with a vulnerability.
In the beginning, there was Vuln. So as you guys know, well, some of you may know if you were here for Anthony, David, and Tim's talk on these aren't the permissions you're looking for. Android has a logging subsystem. It's much like other logging systems, but this one is it. It's accessible via logging APIs or via device, and it requires permissions by an application to access it. Most applications, you use it as a typical debugging system, but there are vulnerabilities that can happen when applications put sensitive information into the logging subsystem and other things can pull it out. So for example, one location disclosure vulnerability that affected Android that Google has fixed in 2.2 Froyo. Their security team was really great about pushing out a patch as quickly as possible. And effectively what it is the location manager, which is the way you access location on the device. It's a system level service. Discloses two key variables. One is the cell ID, and the other is the LAC, the location area code. These are GSM parameters that you can use to locate a person. And so what happens is the location manager logs these variables into the general system log, and an application that doesn't have location permissions but only has read logs permissions can get access to them. So effectively, this is an information disclosure problem.
Right, and conceptually, this class of vulnerabilities, what's so interesting about it is the idea that many operating systems, and Android does a good job of this, notifies the user of what's happening. They say, okay, these permissions are being requested. Now imagine a world where applications ranging from something that's looking at your location to actually credentials of a sensitive application, which we'll talk a little bit more about, could be accessed by an application that doesn't request permissions. So a great example of this type of vulnerability, if everyone saw earlier this week, there was a problem with Citibank's iPhone app actually recording certain aspects of the credentials of the banking application to places that might be accessible either on the device or if synced with the PC on the PC. Now this is a little bit different than what we're talking about with Android, but if you look at conceptually the problem, imagine a world where a financial institution has an application that's inadvertently logging the banking credentials to the log files on the device, and then another application that doesn't have access to any sort of information can actually go grab your banking credentials from this log file and take those and use those potentially maliciously. So you could see that in practical terms, if someone is actually looking in these log files and application developers are not being intelligent about what they're doing with these log files, the ramifications could be very, very significant.
So the vulnerabilities we had just talked about have been previously disclosed, and we're going to talk about a new vulnerability that we came across. On Android, many applications log URLs that they hit to the system log. And this actually includes the Android browser in certain circumstances. On this page, you can see two such log entries. The first is what the browser would do if I typed in www.blackhat.com into the search bar. And the Android has actually a really cool, what's it called, an intent system that basically allows you to kind of swap out who handles any given action. And this is the intent being sent by the browser to the system as a whole to basically resolve a search. What the vulnerability we're going to talk about today is what happens when a third-party application, let's imagine this application uses a web view to implement, excuse me, to implement sensitive functionality, and it starts logging URLs. Let's go to an example, and I think some of you will start to see what happens. So let's imagine we have an app. This app is a standard account access app. You might imagine Facebook or any sort of app that you might log into an account with. It has a web view, and when you open the app, it has a login form. And so what happens there is that when you first open the app, let's imagine this company has a single sign-on system. So the app would send an HTTP request to sso.company.com/form. The server would respond with the HTML to render that form. The user click, types in their username and password. They click OK. And the app will do a post to the single sign-on system in that company. Remember, this is HTTPS, so there are no problems with SSL, right? Everything is safe, hopefully. But let's assume that the username and password is correct, and the server will say, OK, the login was OK, but it says, OK, now that you've signed on to the single sign-on system, we want you to redirect to app.company.com, and we're going to give you a session. And that session is authenticated by a secret key, and we're going to give you that in the URL we give you back. So the application gets this redirection, says, OK, I'm going to go get this URL. Now the server responds with welcome to your account and might set some cookies, so on and so forth. What happens when we look at this from the log side? We see get URL, sso.company.com/form. Seems reasonable, right? We see post. We see the post data, or we at least see the URL of the post. Then the redirect, we see the redirect get URL with the secret token. And remember, any application with the read logs permission can see this. So what would happen if a malicious application reads the logs from the device, uploads it to somewhere, and then somebody uses Control-C and Control-V? Well, we found an application in the wild that used get parameterized session IDs, and all you do is paste it into a web browser, and you are fully 100% logged in.
So just so that everyone's clear, you grab this piece of text, paste it into a browser, and you are logged into the person's account.
Not good. So what's the point? App developers in the room, please don't put sensitive information to the logs. If you're using it for debugging, great. Run through. I mean, even great software houses, people who know what they're doing, kind of haven't quite realized that logs are shared property on a lot of mobile platforms, so don't. Also, web developers, especially if an application is logging or interacting with an API, try to use cookies or other sorts of ways of putting sensitive data places, throwing them in get parameterization, especially if we're talking between applications on a mobile device. That might get logged. It's just safer not to.
One thing I might add just really quickly, we're seeing more and more enterprise deployments where folks will build an application for their own company or own internal uses. This is especially critical if this were to happen where the credentials are allowing you to access enterprise resources. You could imagine what might happen if you build an in-house application that's deployed to smartphones for your own enterprise that was compromised through log files, for example, that would then allow a third party to access enterprise resources. So you could see ranging from a consumer with their own, a social networking account or a banking account, for example, to actually getting through the firewall and accessing enterprise resources.
So the vulnerability, this is all fine and dandy. How do we know what apps in the world have vulnerabilities like this? If we do find something in the wild, how do we know who exploits it? And that's an almost intractable question. And so we asked that question. What if we could, say, pose a question to every single app that we can get our hands on in the world for mobile? And a few months ago, we started what we're calling the App Genome Project, which is basically the goal is to identify as many mobile applications as we possibly can and be able to ask them things, sometimes private things. So what is the App Genome Project, you might ask?
So really what we've put together is, as we understand it, the largest ever mobile app data set in the context of security. So we've encountered approximately 300,000 mobile applications, specifically across the Android operating system and iPhone OS, iOS, by looking at both the iPhone App Store and the Android market. We've dug in and really deeply analyzed about 100,000 free applications and looking at things like metadata and application binaries to actually get a sense for what's going on within the context of these applications, looking at trends within apps that could be suspicious potentially or might be doing something like using a vulnerability or accessing private information, and then being able to use that information to almost fingerprint an app, look at the genome of an app, and ask what other apps share that characteristic to, in a proactive fashion, be able to detect those and respond to that threat.
And we'd love to download paid applications as well. If anyone wants to write a check, I'll be available right afterwards to accept. So quick overview of what we're going to talk about today. We're going to talk about a little bit, why mobile apps matter, why you should care, or why you shouldn't care. What our motivations for, what our goals are for the project. This won't be the last time we talk about this. How did we build it? What's under the hood? What did we find? We're going to tell about 4 stories. I think they're going to be good stories. How do we use the App Genome Project as a security response tool? And I think a lot of you here who are in security response organizations will see how this can definitely help. And what's going to come in the future? We're going to try to whip out our crystal balls. First, why do we care about mobile apps?
So mobile apps matter, and we could talk about why they don't matter also. So I think it's a very obvious to everyone that really smartphones are the computing platform now. It's the future of computing in terms of the just general number of folks who are actually going to be using this as their primary computing platform. It's funny, I look back to when Kevin and I were talking about Bluetooth hacking in 2004, 2005, and the Razr was the most popular device because it was thin, and that wasn't very long ago. And you look at what's changed since then, basically everything. So not only has this computing platform been adopted, and broadly, mobile broadband data has absolutely exploded, which has led to this trend of applications being used, native applications. And we're seeing more and more of the discussion of native applications versus the web, for example. But for the immediate future, absolutely, we're going to see native applications being the primary way that people interact with applications on the mobile platform. And not only are people downloading apps, the people who do download apps are doing so at a voracious pace. So we're seeing on average about 22 apps per smartphone. I can tell you that we've seen a number of data points where people may have hundreds of apps on their smartphone, and especially in a world where a lot of new smartphone users are unsophisticated, this is a brand new platform to them, they're downloading apps just because it's exciting, not even really thinking about what's happening on their device or what might happen in the context of these apps. And most importantly, we're finding apps access sensitive information and can actually cost you money, incur financial damage. So bank accounts are a great example that we talked about. SMS premium billing or premium phone calls. We have actually seen instances of malicious applications on various platforms leveraging premium billing mechanisms like this that one of our friends, Miko, is actually going to be giving a talk on as well. That's a really interesting subset of the types of ways folks can monetize attacks. And then email and text messages, sensitive information.
I think the power of monetization on mobile, imagine if every PC in the world had a UDP protocol where you can send a single packet and money went flying around. I mean, that's pretty powerful from an exploitation standpoint. That's what reverse SMS billing is.
So why should we actually care about this? I mean, first and foremost, standardized APIs are making it easier and easier to actually create practical attacks. So instead of having to do something complex on a desktop-like environment, I know I can just call the contact API, for example, and have a very programmatic, simple way to grab that information. I can do that with billing. There's a whole host of things I can do. And the capabilities themselves, for example, browser history, dialing, SMS history, there's a whole host of things that allows me to get information in a way that enables these attacks very easily. And more importantly than ever, there's a massive incentive for people to actually attack these devices. And we're very early on. I mean, the sky's not falling at the moment, but the platform is evolving so rapidly that the fact that I can directly monetize an attack through SMS or premium rate phone calls or indirect mechanisms such as selling your personal information. So if I grabbed your information and sold that to a spammer, in addition, grabbing sensitive information, we're actually finally seeing the tipping point of that motivation. I mean, hackers in the context of the bad guys, the criminal organizations are lazy, and they will do the simplest attack that nets the highest ROI. As we see the tipping point of it becoming easier on the mobile platform, then we'll see that change from the PC to the mobile device itself. So why won't mobile threats matter? We're skeptical people. We like skeptical people.
John, security people aren't skeptical.
So constantly we hear, okay, well, why should we even care about this? So mobile being fragmented is something we hear constantly, and I agree, mobile is fragmented. But when we look at today's world, how many devices are out there and how rapidly they're shipping. I mean, even a year ago, there was very, very few Android devices. It's absolutely exploding. There's nearly 150,000 to 200,000 Android devices shipping every single day. So when you think about, yes, Windows is this kind of singular platform that it's easier to attack, there's going to be 3 Windows or 4 Windows in terms of equivalent size and single OSs. So when we look at that, you have iPhone, you have BlackBerry, you have Android, there's going to be something that actually forgoes that fragmentation. In terms of sandboxing, yes, there's a sandbox, but sandbox doesn't always mean safe. And in what we've seen OS vendors implement generally is great thinking, and we're super on board with the approach. We just want to make sure that people are tempered in their understanding of what's possible and what's not. And then in terms of attack surface, I mean, the attack surface, yes, in the context of mobile, could be looked at as small, but then you look at things like push services being implemented, messaging services. It's really becoming easier and easier to attack a whole host of things, ranging from the SMS protocol to things on the device itself to third-party services interacting. And we're seeing examples of this with third-party web-based services interacting with things on the mobile device that then serve as a vector. So we may find web-based exploits actually enabling compromise of the mobile device itself.
It's the question of why did we go do all this again? Ultimately, our goal is to keep people safe. I imagine that's why a lot of people do security research, is to help people better understand things. Especially in this kind of brave new world of mobile. We think it is different from the PC, and we think the approaches are probably going to be different from the PC. And I think for everyone involved in this, good data will lead to good decisions. And this is our small contribution to good data. What we want to be able to also do is identify threats in the wild. The vulnerability we talked about before, that's finding things like that. Whether it be apps that are vulnerable or actual exploitation going on, that's really important to us. It's also kind of interesting to look at, because platforms take different security models, and to be clear, different security models does not necessarily mean more or less secure, they just mean different. And one of the opinions that I have is that threats will evolve with respect to the security model, and we can look into the data and see why we think that as well. And also, we want to see what apps are actually doing. And as we know that this is not always the same thing that things say they're doing. And having data to actually help us identify things in the wild that have some sort of mismatches is good. And now we're going to go over quickly how we actually built this thing. Quick to orient everyone, there's 3 main pieces here that we want to talk about. One, we built a distributed crawler. It speaks Android Market and Apple App Store, so it talks directly to these marketplaces and gets metadata and downloads applications. We have a persistent data store, so we can actually analyze things as soon as we get them, or we can analyze them offline, for example, if we have a question we want to ask every mobile app that we've ever encountered. And we also built custom analysis tools because there's really not too much out there to analyze mobile devices, especially when we have talking a lot of OS-specific capabilities that play into the security model pretty heavily. So the crawler. We decided to build a distributed crawler. We first started as just kind of a single-threaded crawler, and we quickly found that analyzing every mobile app in the world can't do in one thread. So we have a job queue, and we have multiple jobs that can each queue other jobs. So first, we go enumerate applications. And this is actually a lot like you going to browse the App Store yourself. So you might go browse a category, and we'll see a whole list of applications. That's the enumeration step. Depending on the App Store, we may have another step to go actually pull metadata. So imagine you're browsing a category, you list all the applications, and you click on the applications, or a specific application, and you get a whole bunch of data about it. That's the second step. And the third step is, if it's a free application, we can actually have our crawler go and download it. And this thing, it's built in Ruby, and right now it's talking to 2 app stores, but don't be surprised to see it talking to more in the future.
And you can see how powerful this is. I mean, we first started just by doing manual research and looking at mobile applications. That's clearly not scalable. Kevin and I, there's not enough Red Bull to fuel that.
But we try.
But when we look at actually scaling that and being able to, in real time, look at every version of every application hitting in real time, not only being able to analyze threats as they come, but threats when we find new research to go look back historically at what happened and what was there, then this truly becomes a powerful tool.
So once we have the data, we're storing the application metadata, so we can actually go search it and do all sorts of fun stuff with it. We're storing that in MySQL. Application binaries we're putting on the file system. If you want to find the fastest way to make MySQL cry, throw a whole bunch of binary data into it. We didn't do that, but in projects past I had tried. Don't. And we're also tracking changes over time. So imagine we have an application, and you have 10 different versions of it. One potential threat vector is you have a great application, you wait till 1 million people download it, then you turn it evil. Right? So, download 100,000 applications. What's next? What are we going to do with all this stuff? So we built some tools. As John said, we quickly ran out of Red Bull, analyzing these all ourselves. We built some custom static analysis tools to actually look at the application binaries. So when we say we have a data set, we're specifically talking nearly 300,000 total applications, but nearly 100,000 application binaries that are active in the marketplace right now. And we're pulling interesting data out of them. The first is classes and methods reference. So these are API functions that the framework or the platform provides. We're looking at what sort of things are actually implemented in the code. On Android in particular, we're looking at permissions that the application has, and then also any sort of strings that are in the application. They're sometimes helpful to look at. We're going to look at Android first. So not only is Dalvik in Iceland, it's also in your phone if you have an Android phone. Dalvik is a virtual machine that's optimized for mobile. It's actually a really cool piece of technology, and you can spend hours reading about it. Not that I've done that. And it's effectively like a Java virtual machine with some kind of unimportant differences for our analysis here. The applications that you download on Android, for example, they are APKs. This is actually very similar to a jar format if you've ever seen a jar. And a jar is basically just a zip. And the main executable inside of an APK is called classes.dex. And this is an executable that runs in the Dalvik virtual machine. The other really important thing inside of an Android application is what's called the Android manifest.xml. It's a binary encoded XML document. It's a proprietary format, not exactly fun to parse, but there's Android framework code that can parse it for you if you need to do that. It describes the permissions that an application has and the application components. And there are some things that are really unique about the Android runtime that actually make this manifest fairly authoritative and important. And I think to understand how we did the analysis, let me go for kind of a brief dive in the Android security model. They did something very innovative, and that's forward declared permissions that are very granular for specific capabilities. So when you install an app, all of the permissions that app can or will be able to use are declared, and they're in front of you, and you get to say yes or no. This is different from a model where you either don't see what an app is doing or you're prompted to ask at a later time. And I think this is a great feature of the Android platform itself. Another really important point that I think these aren't the permissions you're looking for talk hit everyone, and I'm going to hit you guys over the head with it again. Android permissions and security is enforced at the process level, not the VM level. If you find a way to escape the VM and run something native, that's not an exploit, that's the point. That's how Android works, and it actually it solves a lot of problems because, hey, we can run native libraries. We're not stuck writing Java and Dalvik. We can throw stuff to C if we need to. Hell, we can just throw stuff to shellcode, ARM shellcode if we need to, and that's all within the Android permission model. The other nice thing about this is the Android permission model is the Unix permission model. You're a process. If that process needs to access the internet, it just has permission to access the internet on the Unix level. It's actually quite nice. So with that in mind, how did we actually analyze applications? So the first step is looking at package permissions. It is a great kind of gating factor on what Android applications can do. We're going to assume that applications respect the permissions and that we're not talking about a root vulnerability here. If we have a root vulnerability, we have bigger problems on our hand than whether it respects the permission model. And we also do Dalvik static analysis to extract a whole bunch of stuff. And an example question we might ask an app is, does it have a specific permission, and does it reference this specific API in its classes.dex file? And when we actually define questions, we define heuristics effectively. If we want to know if a device reads the device's phone, or an application reads the device's phone number, we say, okay, does it have the read phone state permission, and does it reference the telephony manager get line 1 number? Or we can run other arbitrary analysis on the fly. And I think we want to declare what the analysis we can do and where the future work is. And as we've said, apps shouldn't be able to exceed declared permissions. But if we know specific vulnerabilities, we can look for those as separate things. Also, capabilities can be implemented outside of Dalvik, so native code can interact directly with the IPC mechanism on Android, and apps can pull code directly from the internet. So we're obviously not going to be looking at code that's pulled directly from the internet when we're analyzing a binary statically. We're also not looking at evasive code. If a code is basically encrypting itself or modifying itself in some way, the analysis we're doing right now is not looking for that. Also, raw IPC calls. So if you're hitting binder directly, that's not in the heuristics we're looking at today. We're looking at the vast majority of apps who use the Android framework and are interacting with it. And of course, as we kind of move on into the future, there will be a near infinite amount of work to get more insight into bad things that are happening. So as we mentioned, we also looked at iPhone. The iPhone security model is fairly simple. There's process level sandboxing, and there's what I'll call App Store API enforcement. Namely that in order to get into the App Store, you have to do the right thing. You have to not use protected APIs, and you have to use APIs in a way that Apple deems good, which is not always a 100% silver bullet solution, but it works a lot of times. And also, interestingly enough, they do have ask for certain capabilities, namely location and push. So even though an application accesses the location API, it won't actually access your location unless the user confirms that you can. So like an APK, iPhone applications are really just zip files. The application binary is a Mach-O executable, which is the same executable format on OS X. And it's typically in the payload, and there's appname.app, which is the OS X and iPhone application package convention, and there'll be a Mach-O binary right inside of that. A quick detour into what Mach-O is, so you can kind of understand how we did the analysis. Specifically, the Mach-O header has a series of load commands. Load commands specify how the binary is segmented, what sort of libraries we're linking against at runtime, if there are encrypted sections. Some segments in Mach-O, text is typically where executable code or read-only constants are located. Data is where writable data is. And then the link edit table is where we have all of our dynamic linker and symbol data. If you guys have analyzed PE, a portable executable format, on Windows or other platforms, there's this confusion of section versus segment. In PE, the top level splitting of a binary is a section. In Mach-O, the top level splitting is called a segment, and a segment has many sections. Totally confusing. I don't know why they chose to do it that way, but segment is bigger than section. One of the problems that we have to deal with when we're analyzing iPhone apps is iPhone apps are encrypted. This is DRM. This is to prevent people from pirating apps. Not that it has stopped people from pirating apps, but that's the intention. So I think to understand how encryption works, let's look at how a typical Mach-O executable looks. The 3 LC segments you see, those are the top level segmentation load commands. And on the left side, you see the flat file. It's just a string of bits. And so what we're showing right here is the first step that the Mako loader in the kernel takes to basically map this file into memory. And so basically it takes the segment commands and looks at the file data and the target VM addresses, and it just maps them over. A lot of times you may have a larger VM space than your file space. For example, if you have really large unallocated buffers, it's just a really efficient way. So if I'm allocating a megabyte buffer in memory, I don't have to have a megabyte of nulls in my file, for example. And it's important to note that iPhone binaries, the text section is encrypted. So what do? The second pass that the Mako linker takes is to look at the LC encryption info load command, and will actually decrypt a certain portion of the text segment and map it into memory unprotected. Both OS X and the iPhone do this. If you want the juicy details, all of this is open source. So I haven't seen too much research into how this typically works, but I'd like to see more. I think it's really interesting stuff. So given that the text section is encrypted, what can we actually see? In our analysis, we're not currently decrypting the text section. We do have the link edit table. So we get to see all the symbols in the binary. And basically every application I've seen in the iPhone App Store is very gratuitous in the symbols that it actually gives us. Also, we get to see load commands that show what frameworks we're linking with at runtime. So what are we doing to analyze iPhone apps? Specifically, we're looking at the symbol table, which tells us defined, which are implemented symbols. So if a symbol is defined, it's a class that your application has. If a symbol is undefined, it's a class that your application references. So it may be a framework API. This is true for C functions as well as Objective-C classes, methods, and instance variables. And it's also interesting to note that Objective-C is a strict superset of C, so everything compiles down to C, and it plays really nicely. We're not doing a VM here, for example. And similar to Android, we want to define heuristics to identify features, capabilities, vulnerabilities, for example. And one example of an iPhone heuristic is we can look at whether an application imports any address book APIs that allow you to read contact data, for example. Or we can really just run arbitrary queries against the application data set as a whole. And we're actually able to hit every application on a whole data set in about 5 hours right now on Android and iPhone and run arbitrary queries against it. So that's pretty cool. I mean, you imagine in the PC space, if you were to ask, how do I ask a question about every PC application written? And that's an almost intractable problem. But the fact that we can actually do that in a reasonable amount of time on mobile may not stay that way forever, but it really helps us right now. So the constraints on what we're analyzing here, I mean, as I've said, we're not analyzing the text section. So that limits the amount of automated static analysis we can do without decrypting things. If people find ways to decrypt, more stuff will happen. And we're not looking for dynamically loaded code because the constants are typically stored in text. And also bypassing frameworks via private APIs. A lot of this stuff won't be able to get into the App Store anyway. So we're not able to analyze that right now. And code downloaded at runtime, of course. And if you exploit libtiff, for example, in your iPhone app and you're downloading code at runtime, we're obviously not going to be able to catch that. So kind of to tie it all up in a bow, we download a whole bunch of applications on Android and iPhone, and we built some tools to analyze this data en masse. So we don't have to drink Red Bull and do it manually. And so now, what sort of questions are we going to ask this data? And what did we find? So I'm going to tell a series of stories. The first story is basically how, when we first got this data set, what did we do? We ask a simple question. Are there any apps stealing my contact list? I'm rather worried about myself and my friends getting spammed. And we came up with, wow, 14% of apps on iPhone and 8% of apps on Android are accessing contacts. That's quite a bit. Let's pick one. Let's see why one of these apps is doing this. We first looked at an Android app, a soundboard app. And we said, well, why is a soundboard accessing my contact lists? That's pretty weird, right? So it requests the right contacts permission on Android, and it references the contacts API. Specifically, in this case, it pulled out the URI for the content provider. We would also found it if it had a string for a content provider, if it referenced any content provider or a contact content provider methods. So why is this Star Wars soundboard accessing my contacts, you might add? Well, it turns out I didn't have to spend too long, and I found that you can actually set a custom ringtone from one of the Star Wars sounds. I've got a bad feeling about this whenever John calls me. And in the analysis, this is an excerpt at the bottom here of a tool called Boxmali, which is Icelandic for disassembler. I don't know what it is with Android and Icelandic, but it's a great tool. And so we found that the class definitions themselves showed us that the purpose was to assign ringtones to contacts. Looking at what is actually inside this method, that's the only time we access contacts, and it's perfectly legitimate. And so what's the point? Not all apps that access sensitive data are bad.
Yeah, just to reiterate that, not all apps that access sensitive data are bad.
Not all apps that access sensitive data are bad.
So we'll talk more about vulnerabilities and additional apps that are potentially bad. But I think what's important is understanding what apps can and can't do fundamentally. It's actually a good thing that apps have permissions and can access lots of data. That's what allows us to have really cool apps. So that's important, and we should not be afraid of that. We need to embrace that, as a matter of fact. But what's more important to understand is that we need to, as security professionals, understand what is possible, and then look in and actually specifically look at the details and understand what is bad in the very, very small amount of cases, and then be able to go on broad scale and look at if that's actually happening in the wild to respond to that.
Absolutely. Story number 2. So in that crushing defeat of not having found bad things in the wild, we said, okay, well, what else might something steal from me? Are there any applications looking at my location? And similarly, we found that, wow, there's a lot of applications looking at my location. 33% on iPhone, 29% of all applications on Android accessing location.
Which is crazy when you think about it. A third of all free apps know where you are.
So we started going through these apps. There's a lot of them. And apps that access location but didn't seem to need it. These are things that seemingly anomalous, like the soundboard. We said, why does the soundboard need to access this? And what we actually found is over and over and over and over again, we found that third-party SDKs were the only piece of code in the application that was accessing the location. And we found that actually interesting. It turned out to be third-party advertising SDKs. When you think about it, it makes a lot of sense. An advertising SDK can access your location in order to serve you more targeted ads. It's the Gmail value proposition, right? Gmail looks at your email in order to serve you more targeted ads, and so you don't have to see a giant banner. And people are aware of this. I use Gmail personally. As long as everyone knows what's happening, it's a good thing.
Yeah, it is a good thing.
So when we look closer, one application in particular, we looked at that had the Quattro Wireless SDK. In the Android simulator, we were actually able to pretend we were at 3.1337, and we Wiresharked it, as all good reverse engineering things start with. And we found a plain text HTTP request to ad.quappy.com, which is Quattro Wireless's ad servers. And I broke down the request just so it's easier to read. And sure enough, we have a poorly rounded version of our latitude and longitude being sent in plain text to an ad server. This is really interesting. So let's zoom out a little bit and say, okay, given that an application implements a certain third-party SDK, what is its likelihood to access location? And these are the numbers we came up with some pretty popular third-party SDKs. iPhone and Android. I think it's really important to take these numbers into context, and I think the insights on the next page will put that into context. So specifically, the numbers on Android were generally lower. That is partially an artifact due to how we analyze things. For example, if a developer on Android brings in an ad SDK, and that ad SDK wants to access location, but the developer doesn't request the location permission, the ad SDK doesn't get location.
Which is a really cool aspect of Android, by the way. It's pretty focused on keeping the consumer's data private.
And so our analysis takes that into account. So if an application tries to access location but it doesn't have permission to do so, that application doesn't access location because it can't. On iPhone, for example, an application is only allowed to use location if Apple deems it appropriate. And they actually had a kind of a fairly big issue earlier this year, and they came out with a statement basically saying that they will only approve applications that use location if the application already uses location. So if you download a mapping application or a restaurant locator application, it's okay to have location-based ads there. It's not okay to have location-based ads in iFart, for example, unless that uses location. And so when we wanted to look at the prevalence of third-party code as a whole, we actually found it was quite prevalent on both iPhone and Android. 23% of applications had one of 8 popular SDKs in them, 47% on Android. And and I think this is a good thing in the sense that we're actually seeing developers share code, and we're actually seeing these SDKs get adoption. I think it's very important, and we ask, well, what's the point? Our goal here is that to help people understand what is going on inside of applications, and especially that there's a lot of novice developers who just, hey, I want to develop a mobile application. And I think it's great that the SDKs make it so easy to get a mobile application out in the wild, but we want to make sure that people understand the ramifications of what they're doing. So when a developer brings in third-party code, they don't always know what's in it. And in fact, because it's closed source, even very experienced developers don't know what's in it. But depending on the platform, you oftentimes have a lot of control. For example, on Android, a developer gets to choose permissions. Even though they don't get to write the code, they get to choose what permissions their application requests. So an SDK may just say, hey, copy and paste these permissions into your Android manifest. But you don't have to do that. You get to put what you want. And I think that's the power that with educated developers, we can make smart decisions for what people do. Also, developers need to kind of understand what third-party SDKs are gathering, especially when you're creating your privacy policy and things like that, because it's a developer's responsibility to make sure their users are informed and aware of the type of data that their application collects. And if there's any message we have for developers, it's, hey, pay attention to what you're doing and be responsible with what you're doing. And I think I do want to put my hat off to how some SDK providers have dealt with the situation. They make sure developers understand the ramifications of what they're doing. AdMob, for example, this is an excerpt from their SDK. They default location to off in their iPhone SDK, and they ask developers to carefully consider the privacy issue. And I think that's the exact right way to do this. If we're going to get applications to serve targeted geo-targeted ads, hey, make developers aware of it, and make sure they're telling their users about it. Right. Makes sense. And
one of the lessons here is just we need to see more developers and SDK developers act like AdMob. So AdMob is taking a really good stance in how they're doing this. The question is the million other tiny SDKs that are out there that really haven't thought about this at all that could be exposing users. That's what we need to be aware of. And we really, really encourage developers to take, as much as they do security, users' privacy seriously.
So the lesson we learned today is that developers don't always know what's inside of their apps. And we hope to encourage developers to really pay attention to what they do put inside of their apps. Third story, I Spy. So we found a huge proportion of applications having third-party code, and we found that users and developers don't always know what's going on. What about other sorts of reasons why somebody might want to access sensitive data? Yeah. Are there apps that could be spying on me? And so we actually dialed up our analysis a little bit and said, okay, what sort of apps are accessing all sorts of really gnarly data? Your IMEI, your IMSI, these are GSM identifiers that can be used for fun things. I hope you guys are staying for DEF CON. We'll see the cell phone sniffing talk. That'll be a good one. Yeah. Browser history, contacts, location, and there's a gamut of other things that you can access and people have been talking about. So the first thing we found was an application by a developer called RxS, and it claimed itself to be a system utility. There were multiple apps in the market, and they all had fairly innocuous names, and a lot of them calling themselves system utilities. Android 15X, Android 16X, Android 20X. Sounds like a home exercise plan, I know. And we say that inside the all these applications, they're shuttling a lot of data to mobilespylogs.com/web API. I don't know about you guys, when I see anything connecting to mobilespylogs.com, I get a little nervous. So let's pull out our Icelandic disassembler and look what we see. Ooh, that's interesting. Get SMS details. contact details, URL details, and call contents. Yikes. So what happens when we actually go look at what this site is? Oh boy, it's Mobile Spy. It's our good friend. It's a very popular mobile spy tool. And
who are not our friends.
Depends on whose side of the spying you are on. So actually, what they're doing is they're instructing their users to basically go to the Android market and download these kind of masked applications, which is kind of interesting. You could say that there's a low probability for me to just go download this accidentally, like downloading a system utility that accesses all of my contact and location data. I'm going to immediately click cancel. But there are apps in the market that do something different than they say they're doing. And this is a fairly interesting kind of precedent and not always a good thing. When you have all sorts of apps floating around that do a lot of really gnarly things, but they don't actually tell you up front, hey, we're doing a whole bunch of really gnarly things. The Android permission model mitigates this actually quite a bit in the sense of you can actually see what it's doing. But a lot of users just click OK. I mean, if there's anything we know in security, the affirmative button gets clicked far more often than the negative button.
Right. And one of the great things that we're seeing in the context of Android is there is fine-grained understanding of permissions, and there is the community policing model where in the context where we see bad apps, we have the ability to, in many cases, go ahead and address those and pull those out of the market.
So an aside, there was a great talk at Blackhat DC this year. And there was a proof of concept spy phone application that only actually used permitted APIs, and they accessed a whole bunch of data on the iPhone. I don't think Nicholas tried to get this in the iPhone App Store, but I think it's really interesting. It opened a lot of people's eyes, myself included, as to all of the things that are just right there for an application to take. On iPhone, users don't know all of the granular permissions. The exception is location and push. But generally speaking, all of the stuff he did, there's no user notification at all. Some of you guys might have seen this week.
Or downloaded it.
Or downloaded it before Apple pulled it. There was an iPhone phishing app.
Flashlight, not phishing.
Or sorry, well, you're right, sorry. It was a flashlight application, not a phishing application. Entirely different. Developed by a 15-year-old. He created this flashlight app that looked and felt and quacked like a flashlight app, but also had a functional SOX proxy inside. So if any of you guys have an iPhone, you know that you're not supposed to tether on AT&T. It's a premium service, and so having an app that allows you to tether allows you to get around that premium service. Obviously not something Apple wants to have in the App Store. This application was actually accepted and was live in the App Store. Once everyone found out about it, Apple removed it. I think the really big message here, yes, it's cool that we can tether and like 1,000 people got access to this, but Apple's never claimed to have a silver bullet, and no security person would ever claim to have a silver bullet. They're keeping the App Store safe, but I think it's really important to realize that no security measure is 100% perfect. The fact that a 15-year-old sneaked an application that seemed like a flashlight app, but was actually a SOX proxy into the App Store is very significant. Imagine what the Russian business network could do if they put 10 developers on sneaking something into the App Store. I mean, there's a lot of very interesting things that could happen there. And I think it's important that we all are vigilant in the type of apps we download and not just be complacent to say, oh, Apple is solving security for us, wave the magic wand, we don't need to worry about it anymore. It's up to everyone to keep the ecosystem safe. Lesson learned here is apps aren't always upfront about what they do. It seems obvious, but I think it's worth kind of having people pay attention, especially users who may be tempted to think, oh, it's from an app store, it's from a trusted company, everything is safe in it. And we want to say, hey, it's a lot safer than having nobody helping keep things safe. But there's no user ignorance is bliss that can go on here. Users still need to pay attention and be vigilant. The fourth story, the orange wallpaper. So we found some spy apps in the wild, and those are obviously bad. What other sensitive data could apps be getting? Maybe not knowing where I am, who I call, what I ate, but things that somebody could use to profit or for other motives. Phone number, IMEI, IMSI. There's only a couple hundred of these in the market, so it's actually a fairly tractable problem once we narrow down the applications that actually access these APIs to analyze a few of them. First, we looked at patterns. Are there any developers that have a whole bunch of applications in the App Store? And wow, Jackie Wallpaper has 76 apps, and I don't even know how to say the name, has 8 apps. That's quite a few that all access these same permissions. That seems a little sketchy to me. What are these apps, you might ask? They're all wallpaper. Wait, why does a wallpaper need to... Okay, well, let's not
Guess
distract...
which one is the most popular?
So let's not distract ourselves with silly security questions. I want to get ponies. My phone is pimped. Wait, why again are wallpaper accessing my phone in IMSI and IMEI? It's a good question. So we Wiresharked it. You probably can't read this, but this is what happened when we ran the application. So we installed the wallpaper app, we got ponies, and this HTTP request was sent in the clear, mind you, to a server. My SIM serial number, my subscriber ID, my phone number, and my voicemail number. I don't know how many people in the room actually put their password encoded into their voicemail number, but you might not want to.
Yeah.
Okay, so it's going to imnet.us. Obviously, this is pretty bad for a wallpaper app to be sending all this information off of my phone, but who is it actually sending it to? Secondarily, there were a whole bunch of applications from 2 developers. It actually turns out, digging into a few of these applications, that the offending code is actually the same. And so I don't exactly know why they have the same code in them, but they have the same class, and it's the same implementation, and it's not anything that's documented anywhere in the world that I can tell. What is this sync device info service doing, this mysterious thing? Our friend Boxmolly again, getting the device ID, line 1 number, SIM1, all the data we saw floating over the clear. Okay, so this is our smoking gun. Who again owns imnet.us? Oh, hi. But nobody would download a wallpaper app that reads your phone state and identity, right? Does anyone want to take a guess as to how many downloads in aggregate these applications have? Just throw out a number. Oh, come on, 100,000, go higher than that. Higher than that.
Yeah.
So this is estimated via AndroLib. Caveat here is Android applications only can tell you if they have more than 250,000 downloads. But between all of these applications, these 2 developers, there is a lot of downloads.
And you can see the power of the App Genome project now, right? We find one app, then we were able to leverage that to look at all the apps that do this. So initially, Kevin and I thought, oh, this is only 50,000 people who've been impacted by this. No. When we dug in, it's much more than that.
Be careful what wallpaper you put on your phone. Oh yeah, there's a lesson here. Apps take advantage of stuff. Yeah, who would have thought? So if an application requests permissions and you put it on your phone, you can probably be pretty sure it might take advantage of those things.
Right, and this is something, it's not one platform or another. I mean, this is something that everyone needs to be vigilant about, and this is not just the OS developers, it's developers themselves, security professionals, and consumers. We all have to take this super seriously. Mobile platforms exploding so quickly now that clearly people are looking at this in a way that they're trying to take advantage of it. So if we sit there and don't do anything about it, we're going to see this become pretty common.
So we went through a lot of that pretty fast. So what did we learn here? First, not all apps that access sensitive data are bad. The key thing, yes, we did find some bad things in the wild, but doesn't mean that a soundboard that is accessing your contacts is really doing malicious things. Developers, message to you, pay attention to what you put in your apps, pay attention to what you subject your users to, especially when developers are bringing in third-party code. As a user, apps may not be saying what exactly they're doing. Do you trust app descriptions? Android, look at the permissions. If you're a IT administrator, encourage your users. I mean, education is obviously part of it. Finding bad things and removing them is another part. And educating everyone is part as well. Yeah. And then apps, taking advantage of their capabilities. Obviously, it's going to happen. So we kind of talked about, imagine there's a hypothetical vulnerability. Such a thing will never happen on a mobile device ever. And we want to figure out, 1, are there apps that are vulnerable in the market? 2, is there anything exploiting it? These are pretty good questions to ask. especially during security response. Imagine we disclose said hypothetical vulnerability to a major vendor, and we want to have data about whether people are being exploited in the wild or not to help determine whether we should publicly disclose. Right? This is a very hot topic question. I'm not going to get too far into it. But the idea being that if a vulnerability is being exploited rampantly in the wild and users can do something about it, even though there's no fix, many would argue that it's beneficial to the end user to know about the vulnerability and be able to take a workaround fix. And if we can identify bad things in the wild that are exploiting a vulnerability, that might drive how we choose to guide our disclosure discussions, and having evidence to actually support those discussions instead of speculation as to somebody might be thinking about this, somebody might be exploiting this, so on and so forth.
Right, so I mean, what's so cool? We have real data. Not only can we discover what's happening very quickly, we can respond to what's happening super quickly.
So let's take an example of this account hijacking vulnerability we talked about earlier. On Android, apps shouldn't be able to get around their permissions. We talked about modulo root. And let's imagine we find all applications with read log permissions, right? In order to exploit the hypothetical service we described, you need to be able to read the logs that app spits out. And actually, if you look at the number of applications in Android that request read logs, it's only a few hundred. So it's actually a tractable problem to solve with Red Bull. And so we can automate static analysis to identify code that accesses log data. And we can actually go look at all of these applications. And see, is this a legitimate use of log data? We might find we were looking for vulnerability A, but we really find that it was looking at vulnerability B that we didn't yet know about. But we can also tell if it's targeting our specific app in general. And so that's one example of how you can use this data. And I'm personally very excited about being able to actually ask the entire set, or at least a large set of the applications in the world, about vulnerabilities, and using that during security response.
And this is just the beginning, right? There's 300,000 apps now. What is there going to be? 1 million in the next 6 months? Who knows? And we're going to be publishing more and more on this data set. It's only going to get more interesting.
So we're going to try to predict the future a little bit. What's to come? We have some interesting data about mobile apps right now on different platforms. Where do we think this is all going? So I think the first thing is App Store distribution changes a lot. I think when you're trying to figure out where mobile apps, like where bad stuff is going to happen, you have to look at what app stores will allow and what they won't.
Yeah. And clearly we're going to see obviously less of the traditional viruses that we did on the desktop, but we're going to see more of the gray area, right?
Yeah. How many hours do you think it'll take to remove "this is a virus" app from any app store? I mean, it's going to be removed nearly instantly.
If it even makes it.
If it even makes it, yes. So the question is, there's a lot of really sensitive stuff on your phone. So, effectively there are gold bars in there, and people want to get access to said gold bars. Do you think that people are going to say, oh, I couldn't do what I did before, therefore I'm not going to try? That seems a little silly to me. But the question is, what are we seeing right now that leads us to believe that different sorts of things are happening? For example, apps that seem good but actually have hidden functionality. This flashlight app, I guarantee you, was a wake-up call to everyone, A, who wanted to tether, but B, who's trying to sneak things into the App Store, whether it's just because you want to get access to protected APIs to get someone's phone number, or you want to do something far worse. There was an interesting example of a game on iPhone not too long ago called Aurora Feint. Some of you guys remember it. What it did was it implemented multiplayer by uploading your contact list to a server.
And this is a legitimate development.
Totally legitimate game. Doesn't look so good from a black box perspective. But things like that, how do you know if that application is good or bad? Is that an application that is actually just snarfing down your contact list and going to sell it to spammers? Or is that like some guys who really didn't know how to do multiplayer very well?
Yeah,
it turned out to be the latter, but...
So differentiating between honest mistake, legitimate developer building great games, between someone maliciously trying to spy on you, for example.
And arguably, you may not be able to differentiate between the two. You can say, hey, certain type of behavior is prohibited, but that's a very, very slippery slope, and it can get very, very fuzzy very quickly. And so if an application is good, but either has functionality or has hidden functionality, or hey, let's imagine, let's get this wallpaper app, let's get it on 1 to 4 million phones, and let's push an update into the store. Guess what? We just pushed malware onto 1 to 4 million phones. Yep. And it's a very interesting spreading technique of an application that seems good but turns bad. There are some counter incentives to that. For example, if you have an app that has 1 million users, you may not want to turn it bad. You may just want to make money legitimately. But we'll see.
I also think we'll start to see OS vendors start to try and get on top of the idea of re-requesting permissions with updates, for example, which seems pretty logical.
Yeah. Android in 2.2, for example, does a great thing. They auto-update applications unless the application changes its permissions. So this actually serves to highlight changes in permissions and target people's attention. So you're not going to distract users by looking at permission dialogues if they've already accepted and looking at that dialogue. Only if things changed on an app are you going to look at it. So I think that's actually a great thing. It might mean people will actually look at these sorts of screens. And similar to the spy apps, parenting concerns aside, many would argue that it's legitimate to have an app to see where your kids are. That's how they market themselves, right? But many would also argue that that same app is illegal and immoral and all sorts of things when it's used to spy on a competitor, for example. And do you remove that from the App Store? You might be able to say, hey, it's against our provisions, but you're also removing a pretty legitimate set of functionality from parents, for example. And I think there is this kind of gray area, like with novice versus malicious purposes, that it's going to be very interesting to see how we draw that line on the different platforms in the future. So key takeaways: users, pay attention to what you download. I don't think I can emphasize that enough. Developers, be responsible with the data that you collect and how you use it. And if we see anybody putting sensitive data into the logs and they were at Blackhat, shame, shame, shame. Administrators, you don't want to ban apps on smartphones or smartphones. I mean, they're a great tool. They make people more productive. There's a vuln in Word. You don't put everyone on typewriters for a week until it's patched. We just need to think intelligently about it and figure out how to make these things secure and make the right decisions. Yeah. And our goal is to help give data to help people understand where the threats are and how we can solve them.
And I think it's important just to clarify, just because apps have access to certain parts of data doesn't mean they're bad. We need to look at the context. We need to be aware of them. And I think that as individuals, we need to make sure we're protecting ourselves. But more importantly, I see challenges. I think we get calls from CSOs almost every couple days now asking about, okay, we have consumer devices coming in to our corporate resources. When individuals are making decisions for themselves that then impact our enterprise, how do we think about that? I don't know if we have the answer to that problem yet, but this type of data set, the way we're approaching this, is absolutely the direction that it's going to need to take to actually solve this problem.
So if anyone has their pet questions, private questions that they want to ask mobile applications, we have a big data set and we're happy to ask them. So if you have some ideas on what apps might be doing bad, or if you're curious about behavior of certain apps, send me an email and we'll try to run them. Yeah. And thanks everybody for coming.
Yeah,
it's great.